In this video, we are going to consider the resistance of real ammeters and voltmeters. Usually, we consider meters in an experiment in circuits to be considered ideal. What we mean by this is that we assume that the meters have either, in the case of an ammeter, zero resistance, or in the case of a voltmeter, we assume that it has infinite resistance. Choosing this convention will make sense when we consider what these ammeters and what the ammeter and the voltmeter actually does. The ammeter is placed inside the circuit and the current flows through it. In theory, the ammeter itself should not affect the flow of the current through it. That way, it is an independent observer. It doesn't actually affect the result. The assumption is that the ammeter has zero resistance, and therefore it doesn't affect the current. That's in theory. In practice, all ammeters do have some resistance, and when we're trying to deal with this mathematically, what we do is we assume that the ammeter has a tiny resistor as part of the circuit. We would put an unknown resistor in series with the ammeter, and so our calculation would be done accordingly. Say, for instance, in this question, the current flows through a 12 ohm resistor connected to a PD of 9.1 volts. An ammeter of resistance 0.31 was then used to measure the current. Well, if you place an extra resistance in series with the 12 ohm resistor, then the total resistance would be the addition of these two together. We're treating the ammeter as an extra resistor in series. Voltmeters are a different story. Voltmeters should, in theory, not affect the current at all. What voltmeters do is they compare the amount of energy coming in and out of the circuit, but they should not be drawing in any of the current through themselves. The only way that this can happen is if the resistance of the voltmeter is way higher than the resistance in the rest of the circuit. So high that the best or ideal situation would be infinite resistance. We assume that voltmeters have infinite resistance, so therefore leave the current unaffected as it moves through the components. Of course, in practice, this isn't the case. Voltmeter resistances are indeed very high, but they will always draw a small amount of current through the branches. Now, in order to deal with this in mathematical equations, you would assume that the voltmeter has a small resistor in parallel with the component and the meter itself. Here's a question. Here you're meant to find the current in the circuit before the voltmeter is connected. Then a voltmeter is placed, which has first 5,000 ohms and then 50,000 ohms. Here is the position of the voltmeter. For the first part, you would assume that in addition to the voltmeter, there was another 5,000 ohm resistor in parallel with it. Then you'd work out the voltage across both of those resistors together, working in parallel with each other. So, to sum up, an ammeter that's ideal has zero resistance. However, if it's not ideal, then you assume it has a resistor in series with it. A voltmeter, which is ideal, has infinite resistance. But if it isn't ideal, then you would assume it has a resistance in parallel with it.